Why am I not? There it is. All right. All right. So let's start off by recalling how to deal with complex numbers. How do I add complex numbers? Let me read back up. What is a complex number? Good, as a real number and an imaginary number, right? So how do I add complex numbers? Real plus real, imaginary plus imaginary. Basic combined like terms. That is perfect. So negative 10 plus 7 is 9i minus 5i. That's it. Remember? Oh, flooding back. All right. Now let's multiply. So how would I multiply a single scalar to a complex number? Just simply distribute. Very good. 5 times 2, 5 times 3i. Perfect. Still good? Not scary yet? We then turn complex numbers into vectors, which look like this. This was represented the real part. This represented the imaginary part. Same map, just looked differently. These vectors then turned into matrices. So this is technically what you can also call a 2 by 1 matrix. And on a 2 by 1 matrix, how do I add matrices? Well, in this case, but it has to be the same corresponding element. What if this was a 2 by 2 and a 2 by 1? Could they be added? No. Since they are the exact same size, I'm going to add their corresponding elements, which means this is row 1, column 1 will be added with row 1, column 1. So what's 5 plus 2? Negative 6 plus 7, because again, this is row 2, column 1. Questions? All right. How did I then multiply a scalar to a matrix? By distributing to every single element inside. So what would this give me? Negative 6 and 6. Don't say over. I remember on the last test, a lot of y'all were doing this. Turn them into fractions. They were not fractions. Those are two separate numbers. So negative 6 and 6, technically. Any other questions there? Flashbacks? Feeling better? No. All right, hold on. All right, so two exercises then. All right, so in this one, it says let X equal the matrix 5, 1. We could call it the vector 5, 1. We could even call it a complex number 5, 1. It doesn't really matter. For now, I guess we'll just call them vectors since that's kind of what we're about to get kind of into, but you can treat them as matrices as well. All right, so we say that X is equal to the vector 5, 1. Y is equal to the vector 2, 3, and we want to compute Z in which it is X plus Y. How would I do that algebraically? That's it. You're literally just going to add X plus Y. So if Z is equal to X plus Y, and you know that X and Y is equal to this becomes 5, 1 plus 2, 3, which will give me what? Perfect. Makes sense? All right, then we talked about how to draw this. I am not the best drawer, but I'll do my best here. If I was to draw this, and I'm going to do it this way, and then I'll show you the Desmo way. It comes out cleaner. The first vector 5, 1, remember, is I go on the real axis first. That's what the x-axis represented. So this is the real, also known as x. This was the imaginary, also known as y, depending on what kind of situation we're dealing with. So this is 5, 1. I would put a dot there, but to make it a vector, I would connect it with a line. And just a little arrow there. All right, that's basically telling what, because remember, what does vector do? It does two things. What does vector tell us? Very good. Magnitude and direction, just from like Despicable Me, right? Or was it the other one? It was Despicable Me? Yeah, vector, the orange guy. Yeah, vector. Magnitude and distance. Or distance and magnitude, however he did it. And then you would graph 2, 3. That's 2, 1, 2, 3. Let me do this in a different color. All right, and then we talked about if you could physically move this vector, it would actually go to what you're adding. So if I go to the tip of a vector and I start the tail of a vector, I can then go from here as if it was 0, 0 and actually go over 2 and then up 3. Let's not the best drawer, but these are technically supposed to be parallel and the same distance away. But notice, where did I fall? 7, 4, right? Let me give you a better illustration. All right, if I wanted to do vectors here, I can say, I think you have to use V. But what we get 7, 4? Therefore, there is your vector. Notice in this situation, it is on a two-dimensional plane. So you can almost write it like, there you go. So there's your two-dimensional vector. If you want it, you could even do, see if I could call it X. The original one was 5, 1. That's going to make me do V's. Notice it lands on the same spot. Pretty cool, pretty cool. If I wrote them as separate ones, whoa, stop spinning. Yeah. This. And if we call the next one, take this, move it here, and then it would have the same ending spot as that one. I wonder if I could adjust the settings there. Oh, cool. That would have been a lot easier to know. Here we go. Let's go to -10 and 10. All right, so there you go. So that's a little bit better. So if I could physically take that green one, add it to that blue one, it would land right there on the red one, just like we did last semester. So that kind of makes sense. All right, so graphically, it's not going to be a huge person that's looking for the graph. I don't even think the test looks for the graph, but that's what's happening. So real quickly, do number 2. Just be able to compute z equal to x plus y, given those x and y's. Yes, go ahead. Oh, wonder if it'll let me pick it up. It doesn't let me pick it up. But so let's pretend these are great drawings. Let's just pretend for just a little bit. Like we're in kindergarten, everything was perfect. So just like I moved this purple one to the end of the black, I could have done the same thing, adding the black to the purple. And I could have gone right here. And notice, what shape would this make if this was perfect? A parallelogram, because this would be parallel and the same size as this one. This would be parallel with this one and the same size as well. There's a kind of a parallel, but no matter which way you add them, you would still end up at that result at 7, 4. Yeah, yeah, and it doesn't have to be perfect on the drawing. Obviously, I'm not the best. I was just trying to use Desmos to show it as a better illustration. I just wish it would do a better job of like physically moving it. See if I can do something different. We are working on that. I can't move it still. But oh yeah, yeah, yeah. I wish but if it doesn't give me that authority, to my knowledge, it might. It's not it's not that. Close enough. Does that house have four sides? Square and a triangle? We'll see. All right, so here we go. So when graphing this or when computing it, all I got to do is just add the x plus y. So x plus y, here's my results. -4, 2, plus 1, 3. What do I get? The algebra part is the best or the easiest. You got a parallelogram. 4, 2 would be 1, 2, 3, 4, up 2. So your first vector, give or take, is about right there. All right. And then what I'm going to do is I'm going to then graph 1, 3. Give or take. Here's where my vector is located. And then what I'm going to do also is I'm going to attach the tip to this, the tail to the tip. So that's going to be over 1, 2, 3. So over 1. So again, best illustration of being parallel and about the same size. And then you could have also gone from this tip, the tail, and gone over 1, 2, 3, 4, and then up 2 to land you at the same spot, which is again -3, 5. A parallelogram is a rectangle. A parallelogram just means it has two sets of parallel lines. So a rectangle itself is a parallelogram. So that's what that coordinate right there would be. That would be the answer. So that's the answer we got algebraically. And then these both land at -3, 5, regardless of how you would have added the vectors. The graphing part. Okay, so I started by graphing my first vector at -4, 2. And then from that tip, from that tip, I'm going to start the tail of the next vector. So then from here, I'm going to graph 1, 3 as if that was the origin. So I'm going to go over 1 and then up 3, and it lands me right there. Does that make more sense? And then you could do the same thing. If I went to the other one and I went up over 1, up 3, from that tip, I could have also gone left 4, up 2, and it would still land me right there at 3, 5 or -3, 5. So from the tip of one vector, you're going to treat it as if it was the origin so that you can then graph the next vector. And you can do this with multiple vectors too. We saw it. Go ahead and try 3. I will say drawing is probably the most challenging. If you want to, you think you can do it? Again, I will agree. The algebra part's super easy to do. It's the graphing part that might get us. Number 4. I think you squared it. Yeah. All right, ready? All right, so let's do the math. Again, I'm looking for x plus y. So that's just going to be 3, 2 plus -1, -3. What result does that give me? 2, -1. So what having our answer does for us, it kind of helps us know where we should end up with the graph. But this right here would be graph 1, 2, 3, up 2. Here's my first vector. And then if I graph the other vector, so I go left 1, down 1, 2, 3, give or take about right there. But if I graph that same vector, but at the tip of the other one, I would go left 1, then 1, 2, 3, which would put me about right here. Or vice versa. If I went from the tip here, that would go over 1, 2, 3, up 2. So land you right there, which again would be the coordinate to -1. Is that making a lot of sense? All righty. So yeah, so let's jump to number 4 on the exercise. Do you want to attempt it on your own, or do we need to discuss it? All right, let's discuss it. All right, so we're given that x is equal to 3, 2, and we're asked to compute z as 2x. So let's write that out. So 2x written out would just be 2, and then my x would be 3, 2. So just like in the opening exercise, how do I multiply a scalar to a matrix? Good. You would distribute the scalar to every element in the matrix. So that's what I'm going to do here. And what do we get? 6, 4. Again, algebraically, looks super easy. Let's look at it graphically. What do you think graphically it's going to make? Pretty much a straight line. Notice it no longer says draw the parallelogram here, right? So if I was to graph this, I would say, all right, my original graph is 3, 2, which lands me here. And if I double that, going from this point, I can go 1, 2, 3, up 2, would in fact land me at 6, 4. And so you can kind of see that the line just doubled, which makes sense if I multiply by 2. Questions on these concepts so far? All right. You want to try 5 then on your own? Attempt 5. Don't be scared of fractions. To multiply straight across, yes, sir. Technically, yeah. Well, no. It just should be reduced. Doesn't necessarily mean it's going to be between 0 and 1. That would be if we talked about a unit vector, which we haven't brought up yet, again. All right, we got 5 done. So again, just like before, I'm going to take the 1/3. My thing is lagging. I don't really like it. They gave you nice numbers. What is 1/3 of -6? And it's 1/3 of 3. Very good. So graphically, what happened to your original vector? Oh, that 3 times shorter. Was it still within the same line though? So the direction was the same. We just saw that the magnitude, the distance, got 3 times less. I like that. Perfect. Trying to prevent this lag here. All right, here we go. All right, so that gave us -2, 1. So when we graph it, we first started off with 1, 2, 3, 4, 5, 6. 1, 2, 3. We get a graph right here. And then when we graph that -2, 1, we saw that again went in the same direction, just a third of the size. So technically I could have blamed 3 of those pink lines. We still good? Have we already done 6? All right, so let's check 6. So again, I want z to equal -3 times this matrix. So it's going to be -3 times 1, -1. I keep saying matrix, the vector technically. And so this is -3 and 3. What do you think is going to happen with this one? It's going to be 3 times. Is it going to go in the same direction? Why not? And what did we learn yesterday about negatives? What do we typically saw? A reflection around the origin. All right. So that's kind of what you're going to see here. So I'll start with 1, -1. There's my first vector. And then when I tripled it, but then I also multiplied by the negative, this caused me to go in a different direction. So you can see that it reflect across that origin there, and then also tripled in size. I know this is not up to scale because it looks like 3 lines to my 1, but that's kind of what it's in. Good. Let's see. I'll probably do that better in the thing. So if we have this vector, 1, -1, we get this right here, and then we get this vector. I love how it keeps changing colors. Then I get -3, 3. Notice in a better sense, I could put 3 of these gray lines. It's still going, and then it reflects across the origin, but it's almost in that same kind of path as well. That makes sense? Again, Desmos does a lot better job, so I wanted to use it. Sorry about that. All right, so let's jump to the fun part. 7. Has anyone even attempted 7? Yes. Let's see if we're correct. It's going to be a 3D graph. I thought I get so excited. No, this is stuff. It's fun. This is fun. I feel like I haven't got to deal with a 3-dimensional since I was in college. So getting to teach it now is amazing. Right. Okay. Algebraically, it's still not going to change much. I think it's still just as easy as 2-dimensional because again, as I compute, we know in matrices, how do we add matrices? In their independent or their corresponding elements. So 1, 1 will add up to 1, 1. 2, 1 will add up to 2, 1. 3, 1 will add up to 3. So vectors are the same concept. So if I take my x plus y, which is 3, 1, 1, 1, 3, 1. We're going to add them, not multiply. This will give me what? 4, 4, 2. Perfect. All right. I'm not even going to attempt to try to graph 3-dimensional because I'm just not good at it. So let's go ahead and look in Desmos. Oh, math, everything just disappeared. All right, here we go. Ready? All right. So let's go ahead and change this to 3-dimensional. So again, there's that z-axis now. So you had your x, your y, which is your real and imaginary. But in this case, now we have a z, which makes it pop. I believe they say we live in a 5-dimensional world. Like like the very second and moment that you're in and interacting, this is 5-dimensional. 4-dimensional is just touch and feel. Like you can do that in any kind of sense. But in the moment, you're 5-dimensional. So if you ever go into the future, are you technically in 6 dimensions? Because you're not in the moment, but you're in that moment, but just not your current moment. Oh, talking about wormholes, right? No, it's not. No, that's not conspiracy. That's factual. Right. So that's what I'm saying. So would you still be in 5 dimensions? I don't know. I don't know. Kind of cool. So notice here when I graph 3, 1, 1, notice it is now not quite on the XY coordinate. It is technically, it goes left, it goes right, and then it goes up that 1 dimension. So that last number is going to represent how far it goes in that 2 dimensions. I think that's probably the best way. It almost looks like a sundial, right? So you're kind of looking like that. Maybe you could pull it from the side view here if you wanted to. You kind of upside down. If I can make it go sideways, it'd be nice. I see what's going on. Z is only going to allow me to go up and down. I will. But technically, that would be the quadrant you would be in right there. And there's like 8 quadrants in a 3-dimension. And yeah. So it's you got 2, then it goes 4, and then it goes 8. We talk about 4 dimensions, has 16 different quadrants to land in. All right, now if we take that, let's graph the other vector. Yes, bathroom, that's fine. Oh, absolutely. Yes, yeah. Oh, I'll do it again. So we just graphed 2 different vectors. Notice their direction now. All right. So I went 1 up, 3, and then when I moved up, so kind of like, I don't know. Let's do this first. So when you first graph it in a 2 dimension, you can graph a 3-dimensional object in a 2 dimension. You just can't see that 3 dimension. So this will just be 3, 1. But then when we make it 3-dimensional, you can see that they both went up 1 towards you, almost like it came at you. So see how they're both the same height off that Z-axis there? It's pretty cool. Now, if we take those, we can add them in space. So when we did that, we ended up getting, what was it, 442? So now notice, again, if we graphed it 2-dimensionally, we get 4, 4. Gosh, man, I wish there was a way to, I want to pick it up and move it. I just wish it would let me do that. But if I was to pick these, oh man, that'd just be great if I could do that. Okay, so that's what I was. So what happens is you take this point right here and then this blue point. Let's see. So it still makes a parallelogram, but like in space, not just on a plane. So if I could physically take this green line, I could add it here and it would literally land me here. And I could put the blue line and it would land me right here. So this is your parallelogram it would make. I just wish I could physically move it. There's some programs out there that will let you do that. I think that's super cool. But that's kind of, and you can kind of see they're still going to be in that same linear path, path. So you have a vector that's going, you have another vector going, but when you combine the 2 vectors, it's like it produces a plane through that 3 dimensions. So you can kind of see it here. If I was to cut this out, I would have a single plane with all 3 of my vectors, the 2 vectors I started with, and then the resultant added. So that's kind of how that works. So if I take a vector here, a 3-dimensional vector, another 3-dimensional vector, add them up somehow, regardless of where they land, you would notice that I could take a slice out of the 3D world and it would still be all fall on that two-dimensional plane. So they all fall on the same plane. We just don't have a definition for the plane since it's kind of out in space. Does that make sense? Super cool. Okay. Okay. Do number 8. Good stuff. Know how to plot it? Ooh, do you want to try to plot it? Now on paper? Does it even say to? It does say to plot it. Let's try. Let's try. It does say. So let's see. Okay. It says then plot these 3 points. Here's your X and Y plane. Best way to draw three dimension in a three dimension in a 2 dimension. Make this your 45. As that's your space. So this would kind of go like this. That'd be the Z. And that'd be the X. And this is the Y. So I don't know. I'm not good at. I do remember like an art class where you had to draw like the highway, like it's driving away. Kind of that same concept. So this is like, think of it like shish kebabs. Have you had shish kebabs before? All right, this is the spear that's going through the plane. You can kind of rotate the XY plane like this and kind of think of it like that. So on this first one here, if I graph 3, 1, I would graph 3 on the X. I would go up 1 on the Y. And I would also go 1 on the, gosh, that's hard to do. Because it'd be like, yeah, because you got your regular XY, but your Y is, your Z is like, it's like in the middle, but it's probably not best to scale. Okay, so I see. So you're putting the Z like this, and then your X and Y. Maybe. Let's try that. I'm not against trying things. So this is our Y next. So if we do this way, where now the X and Y is flat and the Z is going up and down, so that would be 3. Oh gosh, this would be 3, 1, up 1. Gosh, that's still, yeah, but it's still so hard to dictate that. Like you're at 1, but then you pulled it up a little, but then now it looks like it's on, 3, 2 or something like that. I don't know. I'll never make you draw a 3 dimension. That's hard. Maybe we could do like the old classic. And then there's like X and Y here, and here's the Z. I think that's hard. That's gotta be hard. Without like a computer program, even they have pictures of like a 3 dimensional program on there. So it's like they didn't draw it either. So I'm not gonna make you draw a 3 dimension. I just think that's super cool. Did you already do number 8? This is why I love my job right here. It did? I have no idea. Let's see. Let's see. All right. So Z equals X plus Y. So that's going to be 3, 0, 0 plus 0, 3, 0. This would actually be graphable because there's not a Z number. Yeah. So what do we get here? So I'm going to use the program because I still think that's way better. So we're going to keep that 3 dimensions there. Three, 0. Oh man, they used gray. Can we use a different color? Can't even see that. It's there, but I can't. Did y'all see? I barely saw it. Yeah. Okay, we got red now. Okay. Okay, so in a two-dimensional plane, obviously this is a 3, 0, so it should be landing on the x-axis. So looking at the z, it's not above or below that xy plane. It's directly on the xy plane. And then we graph this next one, 0, 3, 0. And so here, I used gray again, whatever. Oh, there's blue. So there's my XY coordinate as if there was no Z at all. And then again, because there's no Z on both of them, you can see that neither one of them rose above the XY coordinate. So then when we add the two, and we got 3, 3, 0, notice again, it still does not go into the Z dimension, but it does spread out on that 2 dimension, where if I was to connect the blue with the red, you can almost see better with the square. Stop moving. See the blue right here? I connect it right there. It's a little bit clear if I put the blue and connect it right here and put it on the green. Pretty cool. I think this is so cool. All right. I think we're just about done. We got like 2 more problems and then I'll call it a day. So let's look at number 9. Go ahead and try to compute it and then think about what you think is going to happen. Oh, did I go too far? You will next week. I'm not going to be here Monday, Tuesday, or Wednesday. So y'all, Monday and Tuesday, I'll be in Austin. We leave Friday for the TCEA conference. And then Wednesday, my other part of my job, I have to build the curriculum for 6th through 12th grade, and they're going to give me a day to do it. So a day. I'm going to need more than that, but I can structure my brain and build it from there. Not Monday and Tuesday. And then she's out Thursday because y'all got clinicals. That's what I'm talking about. Oh, I'm talking about next week. Yeah, I'm here the rest of this week. All right, what we get? All right, what do you think graphically this is going to happen? Okay, so, describe what you mean by expand. Okay, dilated circle. Okay, but this isn't a circle. This is just a vector. What's going to happen to a straight line? Is it going to go in the same direction? Yes. Just like with the two-dimensional, it's going to be in the same direction, just be 4 times longer. It's perfect. I got you. I was just you had the right vocabulary. Just put it all together. It's great. So let's look at that real quick, and then we'll do the last one, and then I'll take questions or excitement if you just want to like try experiment things here. All right, so we had 1, 1, 1. So again, you can see now if I graphed it just on an XY plane, obviously just went 1 over 1. In a 3 dimension, is now raised off by 1 unit from the XY plane. And then if I was to multiply that by 4, we see that again, it got 4 times longer on the 2-dimensional plane, but also got 4 times longer in the Z dimensional plane. So it got higher off the XY plane. Make sense? All right. All right. Yeah, have you already done the last one? All right. Just because I want to flip back. This is number 10. We have Z equals negative 1/2 of our X, which in this case is 2, 4, 4. I'm glad they use nice numbers. What's that give me? What do we think is going to graphically happen now? It's going to reflect over the origin, whoever says, still going to reflect over the origin. Our origin is still in the same spot. It's just labeled as 0, 0, 0. And then what was the other thing? Okay, it's going to be that same line reflected over the origin, but be shorter by how much? Half. Very good. So let's graph it real quick to verify our thoughts. All right, so again, if this was just a regular, let's price it up. This would be at 2 comma 4 if it was just a two-dimensional, and then we can see it's now been rows off the XY plane by 4. And then when we half it, actually, I kind of want to perfectly line it up. So right now we're looking at it as 3D. So here's our plane, and then now here is the 3D part. So watch what happens. Notice now it went below the x-axis or the xy axis, and now is in the reflected over the origin concept. But then also notice it's probably about half the original size. And then also you could see two-dimensionally as well that blue is still about half the size as well, still reflected over the origin. Any questions on this? All right, then that's all I got. Any questions?